Alright, so this lesson focuses on vectors in 2 dimensions. We're going to learn how to add and subtract them on paper. 2 basic methods. One is using a ruler and protractor. The other uses trigonometry and geometry. For this lesson, we're just going to set the basics of how you orient vectors on a paper so you can get a better idea of how they are coming together. So if you recall from the previous lesson, a vector quantity such as displacement, velocity, force has 2 basic properties, right? There's magnitude, which is just a fancy way of saying there is an amount. All measurements have that. And then, of course, there is the direction part. Okay. And we represent the direction as with an arrowhead, and we represent magnitude with the length of the arrow. Alright, so we have some representations right here. So let's establish some basic rules. When you're accurately drawing vectors, one must establish a scale. Okay, so if you're asked to represent 5 newtons of force and you want to put that on a paper with the length of an arrow, you got to say something to the effect like 1 centimeter on the paper equals a certain number of newtons, or in this particular example, 1 centimeter on paper might represent 10 kilometers of actual distance if we're doing displacement. Or we could say 1 centimeter of paper equals 5 meters per second of speed. Right, so that should make sense. So the longer the arrow, the greater the magnitude, but the actual magnitude depends on whatever scale you set up. When we want to measure direction, it's nice to have an arrowhead, but we want to be more specific. We could say that this vector up here is pointing left and down a little bit, but that's not very specific. This one is pointing down and to the right, and this one is pointing straight down. What we want to do is get an exact value, so what we have to do is when we draw vectors and we want to indicate a particular direction, we measure that as an angle. And we reference that angle to the directions of the compass. Okay, so this is confusing at first, so pay close attention to the next graph and we'll try to sort this out. Alright, so I have 2 vectors drawn. Okay, we'll call this vector A and we'll call this vector B. And I've got it drawn and I have 4 angles I can look at: theta 1, theta 2, theta 3, and theta 4. Now I want to give the specific orientation of those vectors. So we can see that theta 1 is 55 degrees over from the north pointing direction. So it's not just good enough to say that this vector A is 55 degrees. We have to reference it to either the north or the east line. So what we would say, it's 55 degrees. And if we're referencing it to the north, it's in this general direction of the north, and we'd say that's east of north, right? To go from the north line to where this vector is, we have to head east, so we'd say this vector is 55 degrees east of north. Okay, so again, this angle is between the vector A and the north line, so we're coming east of north. If you looked at theta 2, we know the law of complementary angles that this angle is 35 degrees. Okay, but what's it relative to? Well, it's, again, if we're referencing it to the east line and we moving up or towards the north, then we'd say that's north of east. So we have, with this vector A, there's 2 ways we can state its orientation. We can say it's over from the north, specifically east of north, or we can say it's north of east as we move up from the east. The 2 angles will be complements of one another. So think to yourself right now, then, what would be theta 4 given that that's 70 degrees? We know that's, we're going to put it, I'm sorry, let's go to theta 4 here. We know that's 70 degrees. So what would be our reference to the compass? So take a few seconds and determine what you think that would be. Okay, well, hopefully you reasoned out that we're referencing this particular angle to the south, and so we're moving to the left or westward of south, so this would be 70 degrees west of south, and therefore theta 3 would be the complement of that, 20 degrees south of west. Alright, so we'll get a little bit more practice with this, but it's critical that you understand how to not only measure angles, which we assume you do, but how to reference it to the compass directions. Alright, next, how do you add vectors when you have multiple vectors? Okay, so if we represent vectors with arrows and we have multiple and we want to add them up, let's say displacement vectors, the general idea is we want to connect them from tip to tail, etc. So if I'm starting right here, okay, here's my first vector, I've represented it like this, I'll call this vector 1, and then to it I add vector 2. In other words, I started here on 1, I ended here on 1, so if I'm going to start my next part of my addition, I'm going to start at the end of 1, go to here, that's the end of 2, 3 begins at the end of 2, the tip of 3 is at the tail of 3 is at the tip of 2, so on and so forth. Okay, so I have these 4 vectors connected tip to tail. Now I want to find the vector sum of all those. Okay, so the vector sum is the beginning of my first vector, which in this case is vector 1, and it's to the end of my last vector, which is vector 4. So I draw a vector. If I had a ruler, that would be nice. Okay, but you get the idea. And that I'm going to call R. Now, R represents the vector sum, and the technical name for that is resultant. Oops. Sorry for that mistake. That should be resultant. Okay. And that's really just another way of saying vector 1 plus vector 2 plus vector 3 plus vector 4. Eventually we'd measure the magnitude of this, but right now I want you to understand the orientation. So what angle is this pointed right now? So I need a reference. I think on your sheet there's a little line that's down here. That's the south direction right here. So we can see that this is towards the south, and if we draw on this reference, it's also towards the west. So somewhere between south and west. So if we estimate this angle, it's roughly halfway between. So we say it's roughly 45. We'd get a protractor if we needed to get the exact measurement. And since this is the angle that I'm measuring it, I'm going to say, all right, the angle is referencing to the west. It's between the west and the resultant, and we're headed south of it. So we're going to say south of west. That's just like we saw with angle 3 up here. Okay, so again, to reiterate, when you have 4 vectors that are just given to you and you want to add them, you place them tip to tail, tip to tail. The order does not matter. The commutative law of vector addition is the same as the commutative law of scalar addition. So no matter which order you put them in, you'll always end up at this place if you started up here. All right, just a few more things, and we'll finish up. Okay. Now, what happens when our vectors are drawn tail to tail, like in this example here? Okay, we'll call this vector A, we'll call this vector B. We want to, how do we add them? Well, we want to move them tip to tail. So what I can do is I can pick up A, because it doesn't matter where it is on the paper, but if I want to add them graphically, I want to pick up A and place it at the end of B. So I'll put that there, and there's A. Or I could pick up B and put it at the end of A. It doesn't matter. Whoops, try to get this nice and straight. Either way, notice that we end up at the same spot. So my resultant, okay, would be the beginning of one of the vectors. Let's say the beginning of this B. I'll call this, whoops, I'll call this B prime. I'll call that A prime. So let me erase this. So if I start at the beginning of one of the vectors, let's say B, I follow B, then I went up to A prime and I ended there. Or I could have started with A and gone to B prime. Either way, it's the same thing. This represents the resultant right there. That's the vector sum of A and B. Okay, now we call this the parallelogram method because if you notice, we end up with a parallelogram to help us figure out where the resultant is. So if I then ask you what's the angle of this resultant, if we're approximating it, just to give you an idea, I can choose any angle at the beginning. So I look at my resultant vector, okay, and I always reference it to the beginning of that vector. So I'm going to choose this angle right here. Okay, I could have chosen that angle as well, but if I go at this angle, I see that it's, if the B vector is pointing east, then I'm up from the east or north of the east, so I'll say that's roughly 20 degrees north of east. Okay. Okay, if I chose this angle right here, then I would say it's roughly 70 degrees east of north. Alright, so let's try this one. We'll call this vector C and vector D. So again, they're tail to tail. We can't just draw the diagonal. A very common mistake is to say the result in the sum of those two is the diagonal from tip to tip. It does not work like that. That would give you both the wrong magnitude and the wrong direction. So you have to take your time and think this through. So we can do the parallelogram method. I'm going to make a parallelogram out of these two. Mine's going to be kind of crude. Okay, so that's supposed to be parallel to D. And then I'm going to try draw a line that's parallel to C. Okay, so the vector sum of C and D would be starting at right here, the beginning of either one, and going and drawing that diagonal right there. I have to put an arrowhead on it because it's a vector. Okay, I'm going to call that R. R represents C plus D. Okay, and if I want to estimate the angle, now this is a tricky part. I don't want to measure the angle between R and C. I want to measure an angle between R and one of the cardinal directions. So I'm going to draw in a little line right here. This represents north. This represents south. I measure from the beginning of R to one of those points. So I'm going to go to the south line. Okay, and I can estimate that angle. Looks like, let's say, 30 degrees. And if this is south referencing, then we're going right of it, which is east of it. So that's east of south. Okay, so why don't you try the next one on your own. I'll wait a few seconds for you to try to reason it out. So give it a go. Okay, so what you should have drawn is something roughly like this. I'm going to make a parallelogram. Right, that's not the best, but the idea is the resultant splits the two, and it starts at the beginning of one, ends at that vertex. Okay, so at the very least have that as your R. Now to get the angle, you gotta kind of draw a reference. I'm going to draw a horizontal, and that's the west. I'm going to measure that angle right there. If this is west, I'm going to say I'm up from the west, about a little bit north of west. And it's a small angle, so let's say 15 degrees roughly. Okay, so if you have any questions on this method, make sure you ask in class. The last thing I do is the most difficult of all, but it's just a variation we do it, and that's how to subtract vectors. So suppose I have vector A and B, and I don't want to add them. The addition, I'm going to draw it right now, just to get it out of the way. Here's my parallelogram, roughly, and that is R. I don't want R. I want the difference between the two. So to subtract vectors, we want to make it an addition problem. Okay, A minus B, we know in math, or one number minus another is the same as A plus a negative B. Okay, so now I'm going to make this an addition problem. So to do that, let me change colors. I got to leave A as it is, but now I got to draw negative B. And negative B is B just in the opposite direction. So if I take my B vector and I turn it around, I just put the arrowhead there. Here is now negative B. Let me trace that in red. Okay, that's not a very good arrowhead. And so you can see negative B and A are connected tip to tail, so I can start at B, negative B, and go down to A, and that vector represents, I put an arrowhead there at the end of the vector, that's A minus B. Okay, and if you notice, it's just the opposite diagonal as the resultant. So if we want to do D minus C, I want to transform that to D plus negative C. Now go to this, draw negative C, so I'm going to put an arrow at the other end. There's negative C now. And again, they're tip to tail, so all I can do is go at the start of C and go to the end of D, and that represents C minus D. Okay, so there's a quick summary of how to add and subtract vectors in a graphical approach, and then we'll see how this can be useful when we do trigonometry.